Hi there. Let's now deal with, now that we know about the particle theory, let's deal with expansion, contraction, and then looking at heating curves. If you look in everyday life, you'll notice that there are certain building things that demonstrate that we need to understand and plan for heat. So railroad tracks, for example, when we put them down, we have gaps. This is a bridge deck, and it has a spacer joint. When concrete sidewalks are laid down, they're not laid down all in one complete sort of thing. There are gaps here, and there's reasons for this. From what we know about the particle theory, we know that as particles heat up, they move quicker and quicker and quicker, and they start to stretch out and expand. If these sidewalks don't have little gaps or spaces in them, then they'll start to buckle up. Same with a bridge. The bridge deck needs some spacer joints so that in the summertime, if it expands and stretches out, it won't heave or buckle. And of course, railroad ties are the same way. You can see expansion and contraction. For example, if we look at how telephone wires are hung, we'll see that in the wintertime, look at these telephone wires. They're really tight. However, if we look at telephone wires in the summertime, we'll see that they sag. And again, this is the particle theory at work. During the wintertime, these telephone wires are going to contract, take up less space, and they'll be really tight. However, the particle itself doesn't get bigger, but the spaces between the particles will get bigger and they will expand in the summer. Let's look at a heating curve. Last time we talked about how substances go from one state to another. If we graph what goes on here and we measure the temperature of a substance like water over time, here's what we notice. We take a block of ice at minus 50 degrees Celsius and we heat it up over time with a blowtorch. Eventually, after a minute or so, that ice cube will melt. And when it goes through a phase change, it doesn't change temperature. So water changes state at 0 degrees Celsius. Notice the temperature doesn't go up even though we're applying heat. And so this plateau is what it's called, tells us that the substance is undergoing a phase change. And the heat energy is being used to break the bonds between solid particles so that they're far enough to become a liquid. And eventually when it's all melted, we'll get a temperature change again. So now we get the water's warming up, it's changing temperature, but then it will plateau again to go through a second phase change till eventually now where my pen is, it is in steam or water vapor format. So these plateaus on heating curves tell us when substances are going through phase changes. Phase change here. Now the phase changes, the plateaus may not occur always at 0 and 100. So if I draw a little graph here, for example, and this is time, and this is temperature, and this is 0, and this is 100 degrees Celsius. Watch what a heating curve might look like for salt water. Salt water is going to plateau at a temperature much lower than 0 when it melts, and then salt water boils at a much higher temperature. So salt water's plateaus would be above 100 for the boiling point, and it would be below 0 for the melting. Why? Because we know salt water does this. Salt lowers the freezing point and it raises the boiling point. Let's talk about altitude. Water boils depending on altitude at different temperature. The higher up you are, the lower the boiling point. So if you're up on a tall hill in Denver, it's going to boil at 96 degrees. If you're in New Orleans, sea level, water boils at 100. If you're way up in Mount Everest, water boils at 72.